March 17, 1945. The Rhine River, Germany. Lieutenant Colonel Harvey Fraser stood on the western bank, watching his engineers work under relentless German artillery fire. The notebook in his weathered hands contained calculations that defied everything the Wehrmacht believed about Allied capabilities. 27 hours. That's how long it had taken his men to construct a 969-foot floating bridge across one of Europe's mightiest rivers, while enemy shells screamed overhead. In Berlin, German High Command had calculated it would take the Americans at least a week to build such a crossing, assuming they survived the constant bombardment. They were wrong. Through his field glasses, Fraser could see German observers on the far shore, their binoculars trained on something they couldn't comprehend. Standardized steel panels, each weighing just 570 pounds, were being assembled by teams of 6 men at a time. No cranes, no heavy machinery. Just human hands, portable components, and an engineering philosophy the Germans had dismissed as impossible. The bridge was already carrying 40-ton Sherman tanks across the Rhine. What the German engineers didn't know was that this moment represented the culmination of a revolution in military engineering that had begun 4 years earlier in a small office in Christchurch, England. A revolution born not from complex machinery or advanced technology, but from elegant simplicity. The kind of simplicity that would prove impossible for German forces to destroy, no matter how many bridges they demolished, no matter how many tons of explosives they used. This is the story of how American engineers used modular design principles to build bridges the Germans couldn't destroy. How a British civil servant's hobby became the weapon that broke the Wehrmacht's defensive strategy. And how the simplest solution became the most powerful tool in the Allied arsenal. The mathematics of Allied victory were being written not in grand strategies, but in the portability of steel panels and the speed of their assembly. The Germans had destroyed thousands of bridges across Europe, from Tunisia to the Rhine. They believed they had bought themselves months, perhaps years, of defensive time. They were about to learn that American engineering ingenuity had rendered their entire demolition strategy obsolete. The crisis began in May 1940. Dunkirk had fallen. The British Expeditionary Force had escaped across the Channel, but they had left behind nearly all their heavy equipment. Britain now faced the prospect of defending an island against invasion, while simultaneously planning an eventual return to the European continent. The problem was stark. Every British military engineer knew it. Their existing bridges couldn't carry the weight of modern warfare. The Inglis Bridge, designed during World War I, could support just 19 tons. The new British Matilda medium tank weighed 23 tons. The Churchill heavy tank, still in development, would weigh at least 40 tons. American Sherman tanks, when they arrived through Lend-Lease, would weigh 33 tons. The mathematics were brutal and undeniable. Britain's entire bridge inventory was obsolete before the war had truly begun. At the experimental bridging establishment in Christchurch, a small team of civilian engineers gathered for an emergency conference in February 1941. The directive from the War Office was clear. Design a bridge that could support 40-ton tanks across spans up to 200 feet. Make it portable enough to transport in ordinary trucks. Make it simple enough that infantry could assemble it under fire. Make it strong enough to withstand artillery bombardment. And have working prototypes ready within 3 months. The requirements seemed contradictory. Strong bridges required heavy materials and complex engineering. Portable bridges were light, but weak. Quick assembly meant simple designs, but simple designs couldn't handle modern tank loads. Previous military bridges required cranes and specialized equipment. The engineers had been given an impossible task. Donald Coleman Bailey sat quietly in the back of the room listening. At 39 years old, he was a civil servant with the experimental bridging establishment, known more for his meticulous attention to detail than for revolutionary thinking. He had joined the War Office in 1928, spending 13 years designing military equipment, pontoons, cranes, pile-driving rigs. His colleagues knew him as competent, thorough, and somewhat reserved. Few knew about his hobby. Since boyhood, Bailey had built model bridges from wood and string. In his home workshop, he tested different configurations, different stress loads, different joining methods. In 1936, he had even submitted a proposal for a modular military bridge. The War Office had filed it away and forgotten about it. But Bailey hadn't stopped working on the problem. For 5 years, in the evenings after work, he had continued refining his design. The breakthrough came from a simple observation. Every previous military bridge tried to be complete in itself. Engineers would build an entire bridge structure, then attempt to transport and install it as one piece. This required heavy equipment, careful handling, and substantial time. Bailey's insight was radical in its simplicity. Don't build a bridge. Build a bridge-building system. On February 14, 1941, Bailey received a letter from the War Office. His old proposal had been rediscovered. He was ordered to prepare a full-scale working prototype for testing in May. He had less than 3 months. Bailey didn't sleep much during those months. The prototype that emerged from Christchurch in May 1941 looked deceptively simple. Rectangular steel panels, each 10 feet long and 5 feet high. Crossbeams called transoms. Floorboards called stringers. Each component could be carried by 6 men. Each component could fit in a standard 3-ton military truck. Each component used standardized pin connections that required no special tools. The genius was in the modularity. Need a longer bridge? Add more panels. Need a stronger bridge? Stack the panels in multiple layers, creating triple-single, double-double, or triple-triple configurations. Need to cross a wider river? Add pontoons beneath the panels. The same components could create a bridge 20 feet long or 2,000 feet long. Could support 10-ton trucks or 60-ton tanks. Could span dry gaps or flowing rivers. The May 1941 trials at Christchurch became legendary among British engineers. Bailey's bridge was tested against every existing design. The Inglis bridge required 4 hours to assemble with specialized equipment. Bailey's bridge was erected in 1 hour by regular infantry. The Callender-Hamilton bridge could carry 26 tons but required cranes. Bailey's bridge carried 40 tons using only hand tools. The engineers stress-tested Bailey's design to destruction. They loaded it with progressively heavier tanks. First a Matilda at 23 tons. The bridge held. Then a Churchill at 40 tons. The bridge held. Then they filled the Churchill's interior with scrap iron to add even more weight. The bridge held. When it finally failed, the load exceeded 70 tons, far beyond any military requirement. Field trials began immediately. By December 1941, the first production Bailey bridges were issued to Royal Engineer units. By July 1942, production had reached 25,000 panels per month. Over 650 British companies were manufacturing components, from major steel mills to small machine shops. The genius of Bailey's design was that the parts were simple enough for any competent manufacturer to produce, yet precise enough that components from different factories were completely interchangeable. A pin manufactured in Birmingham would fit perfectly with panels made in Coventry. Transoms from Glasgow worked seamlessly with stringers from London. This interchangeability would prove crucial when American factories began production. More importantly, it meant that damaged sections could be replaced without dismantling entire bridges. Engineers could carry spare panels forward and swap out damaged components under fire. The first combat test came on November 26, 1942. 237th Field Company Royal Engineers were advancing through Tunisia with Montgomery's 8th Army. They reached the Medjerda River near Medjez el Bab at nightfall. German forces had demolished the existing bridge. The river was 100 feet wide, running fast with winter rains. Montgomery's advance schedule called for tanks to cross by dawn. In peacetime, engineers would have spent days surveying the site, calculating loads, planning the construction. There was no time for that. The engineers had 12 hours. They worked through the night by lamplight, assembling panels on the western bank, then pushing the growing bridge structure across the river using rollers. German patrols probed the position. Artillery fire landed periodically along the riverbank. The engineers kept working. At dawn on November 27th, the first British tanks rolled across the completed bridge. Montgomery's offensive continued without delay. German commanders were stunned. Their intelligence had reported the bridge destroyed. According to their calculations, the British would be delayed at least 3 days, possibly a week. Instead, armour was already across and advancing by sunrise. How was this possible? The answer was being demonstrated at dozens of river crossings across North Africa. At Leonforte in Sicily, Canadian engineers built the first Bailey Bridge under direct enemy fire. German machine gunners had clear lines of sight to the construction site. Mortar rounds landed among the working parties. The engineers took casualties but kept assembling panels. The bridge was completed in 6 hours. German defenders abandoned their positions when they saw tanks crossing almost before the last panels were connected. By the end of the North African campaign in May 1943, British and American forces had built hundreds of Bailey bridges. German commanders began to understand they were facing something new. The Wehrmacht's standard defensive strategy relied on river barriers. German engineers were trained to thoroughly demolish bridges during retreats. They used massive amounts of explosives, often destroying not just the bridge spans but the supporting piers as well. The theory was sound. Without bridges, Allied armor would be stopped at every river, buying time for German forces to establish new defensive lines. The theory failed because of one crucial miscalculation. German engineers assumed Allied forces would need to rebuild permanent bridges. Traditional military bridges required extensive site preparation, specialized equipment, and significant construction time. A destroyed bridge should delay an advancing army for days or weeks. But Bailey bridges didn't need permanent piers. They didn't require extensive site preparation. They could be built by infantry with hand tools. Even more frustrating for German forces, Bailey bridges could utilize the rubble of demolished bridges, those stone piers the Germans left standing, perfect support points for Bailey panels. Those concrete abutments? Excellent anchor points. The more thoroughly the Germans demolished their bridges, the more material they left behind that Allied engineers could incorporate into new structures. Destruction became construction material. The United States Army officially adopted the Bailey Bridge system in early 1942, designating it the Portable Panel Bridge. American production began with contracts to Detroit Steel Products Company, American Elevator Company, and Commercial Shearing and Stamping Company. By mid-1943, American factories were producing 20,000 panels monthly. The standardization that made British production work created an unexpected challenge. American manufacturers working from British specifications discovered that different factories had slightly different interpretations of tolerances. The problem emerged in North Africa. An American engineer unit tried to use panels from two different manufacturers. The pins didn't quite fit. The holes were off by fractions of an inch. Eventually, 850 American-manufactured bridge sets had to be tracked down and marked as standalone systems, incompatible with other sets. It was an embarrassing discovery that highlighted the precision required for true interchangeability. British manufacturers, with more experience in quality control for military specifications, had maintained consistency across hundreds of factories. American production eventually matched this precision, but the learning process took months. The Sicily campaign in July 1943 demonstrated both the power of the Bailey system and the desperation of German defensive efforts. As Patton's forces drove toward Messina, German engineers demolished every bridge along the coastal highways. The demolitions were thorough and professional. Bridges were destroyed at their weakest points. Approach roads were mined. Riverbanks were pre-registered for artillery fire. American engineers responded by building Bailey bridges at a pace that shocked German observers. A bridge destroyed at dawn would carry traffic by sunset. In one remarkable instance near Randazzo, engineers discovered that German forces had destroyed a bridge so completely that even the piers were gone. They simply built a longer Bailey span, stretching the bridge from one intact section of approach road to the other, bypassing the destroyed section entirely. The bridge was in operation 24 hours after American forces reached the site. 3rd Infantry Division engineers rebuilt 37 demolished bridges during the Sicily campaign. The average construction time was 8 hours. This included sites where German forces had destroyed not just bridges, but entire sections of mountain roads carved from cliffsides. In those cases, engineers built Bailey bridges spanning the gaps where roads had been. Tanks that should have been stopped for days were rolling forward before German headquarters even received reports of the original demolitions. The Italian campaign, beginning in September 1943, became a marathon test of Allied engineering versus German demolition. Italy's geography favored defense. Rivers ran perpendicular to the Allied line of advance. Mountains channeled movement into narrow valleys. German forces under Field Marshal Albert Kesselring executed a textbook fighting withdrawal, making maximum use of terrain and demolitions. Kesselring's strategy was brilliant in concept. German forces would establish strong defensive positions behind major rivers. They would delay Allied advances long enough to fully prepare the next defensive line. When pressure became too great, they would conduct organized withdrawals, destroying every bridge, mining every road, and demolishing every structure that could provide shelter. Each river should buy at least a week of time. The Volturno River north of Naples was the first major test of this strategy. German engineers destroyed 11 bridges along a 30-mile front. They demolished approach roads, They flooded low-lying areas. They created what appeared to be an impenetrable barrier. British and American forces reached the river on September 30th. By October 2nd, 7 Bailey bridges were operational. German defensive plans that assumed a few weeks' delay collapsed in 48 hours. The pattern repeated at the Trigno River, the Sangro River, the Moro River, the Garigliano River. Each river represented days or weeks of German preparation. Each demolition was thorough and professional. Each delay lasted hours instead of days. At the Sangro River, German forces destroyed 19 steel spans, but left 14 stone piers intact. British engineers used those piers to support Bailey bridges. What should have been a multi-week construction project was completed in 4 days. The psychological impact on German soldiers was profound. Corporal Hans Müller, serving with the 15th Panzer Grenadier Division, wrote in a letter captured by Allied intelligence, "Our engineers tell us they have bought us 3 days. We dig our positions. We prepare our defenses. We watch the river. The next morning, American tanks are crossing on bridges that appeared overnight. How do they do this? Our commanders say it is impossible. But we see it with our eyes. They build bridges faster than we can destroy them. What is the point of defense if every river is crossed before we can prepare the next line?" This erosion of confidence in defensive capabilities affected German morale throughout the Italian campaign. Soldiers stopped believing that rivers would protect them. They stopped trusting that demolitions would buy them time. When defensive plans consistently failed to provide the promised delays, faith in leadership deteriorated. The Winter Line, officially the Gustav Line, represented Kesselring's most ambitious defensive effort. Anchored on the monastery at Monte Cassino, the line exploited rivers, mountains, and prepared fortifications. German engineers spent months preparing the positions. Every bridge for 20 miles in either direction was pre-wired for demolition. Every approach was covered by artillery. The defenses were as strong as engineering could make them. The Gustav Line held longer than previous positions, but not because of demolished bridges. It held because of terrain, weather, and fierce German resistance. Allied engineers built Bailey bridges across the Rapido River, the Garigliano River, and numerous smaller streams. The bridges appeared as quickly as anywhere else in Italy. What slowed the Allied advance was mud, mountains, and German soldiers fighting from prepared positions, not destroyed infrastructure. The Rapido River crossing in January 1944 demonstrated both the horror of opposed river crossings and the determination of combat engineers. The 36th Infantry Division attempted to cross the Rapido in assault boats, establish a bridgehead, then allow engineers to build Bailey bridges for armor support. German defenses were formidable. Pre-registered artillery covered every foot of the riverbank. Machine guns had interlocking fields of fire. The river itself was fast, cold, and difficult to cross. The infantry assault became a catastrophe. Boats were hit by artillery before reaching the water. Those that launched were swept downstream by current or riddled by machine gun fire. Engineers trying to build footbridges worked under continuous fire. 4 footbridges were planned. Only 1 was completed before being destroyed. The attack failed with nearly 1,700 casualties. But even in this failure, engineers demonstrated extraordinary courage. Technical Sergeant Anthony D'Amato led a bridge-building crew under direct fire. His official citation, preserved in National Archives, describes the action. Sergeant D'Amato led his squad to the riverbank at 2,200 hours. Despite heavy artillery and machine gun fire, the squad began assembling a footbridge. 3 men were killed in the first 10 minutes. Sergeant D'Amato continued directing construction. At 2,340 hours, artillery fire destroyed the partially completed bridge. Sergeant D'Amato immediately began constructing a second bridge at a different location. At 0130 hours, this bridge was completed. Infantry elements crossed until 0300 hours when enemy fire destroyed the bridge. Sergeant D'Amato's actions enabled over 200 infantry soldiers to cross and establish positions on the far bank. D'Amato survived the Rapido crossing, but was killed 2 months later while building a bridge at Enzio. His story exemplified thousands of similar stories of engineer courage throughout the Italian campaign. They built bridges knowing they were under observation. They worked knowing artillery could land at any moment. They continued after casualties because soldiers needed bridges more than engineers needed safety. When the Gustav Line finally broke in May 1944, it broke not because bridges were built faster, but because overwhelming Allied firepower and determination eventually overcame German defences. But once the line broke, Bailey bridges enabled rapid exploitation. Within days of the breakthrough, Allied armour was racing toward Rome. German forces attempted to establish new defensive positions at each river, but Bailey bridges appeared faster than defensive lines could form. The capture of Rome on June 4, 1944 showcased Allied engineering capability on a grand scale.